I'm Don Cornwell. Thank you for that wonderful introduction. I have the program responsibility at NASA headquarters for our Optical Communications Program, and I'm here to tell you about some exciting breakthroughs that we've had in the last few years in optical communications that's really excited the management within NASA, and I think with the rest of the world as well, and allowed us to get really support for a more vibrant program, and that's what I'm going to tell you about today. But I'm also going to fill you in a little bit on the success of the LLCD mission a bit more. I want to say that laser communications, the thought of it has been around probably since Charles Towns invented the laser with his colleagues and other folks that did that as well. And for decades and decades, laser communications was attempted. Programs would start in the various space agencies, and I'm talking about free space optical communications. We're doing it in fiber all the time, of course. And then these programs would run into some sort of issue or a funding issue, and then they would be canceled, and they would be basically underground for a while, and then they would pop up again in about another 10 years. So in the last decade, we've finally broke threshold, no pun intended here, in a laser group. And I think that we're off and running at this point, and we're going to make these viable systems that we're going to be using in operations going forward. So on my chart here, you can see some of the various programs I'm going to talk about. But first, why does NASA care about free space laser communications? We've been using radio for the last 60 years. Why isn't that good enough right now? And that's because we need more bandwidth, more and more bandwidth to bring back more data from the instruments that we send out in space. This is a really interesting example here. Here's an image of one of our Mars rovers taken at 30-centimeter resolution on the edge of Victoria Crater, which is on Mars. And this is a little-known fact, but if we wished to transmit a 30-centimeter resolution Google map of the entire Martian surface at just 1 bit per pixel, using the current best RF system that's been flown to Mars, it would take up to 9 years. That's 6 megabits per second using Ka band when Mars is at opposition, when it's at its closest. So the point of this is that we're leaving 90% or more of the data on the surface of Mars or in orbit of Mars, and we're having to pick and choose, and I think we're missing moments of serendipity because we're not bringing that data back. But with the advent of optical communications, we could do that in 9 weeks. We could do that entire Google map in 9 weeks. So we see that LaserComm's breakthrough high broadband technology is going to allow us to break through these bottlenecks that we have. So NASA's first mission for LaserComm was the Lunar Laser Communications Demonstration mission. We first operated from the moon in October of 2013. You can see here we have in addition to the concept, which is basically the spacecraft that we flew on, a laser link back to a ground station on the Earth. And you heard some of the numbers earlier. I'll talk about that a bit more. But we were nominated actually for the Collier Trophy in 2014, which is a trophy for the most outstanding achievement in aerospace, and it's awarded by basically an airplane club, the NAA. And so we were nominated. We didn't win. We lost to an airplane, which I guess was kind of expected, but we were just happy to be nominated anyway. And of course, this project was really led up by the technology developed by MIT Lincoln Laboratory with NASA Goddard, NASA Ames, NASA JPL, and also the European Space Agency participated with us as well. So what did we actually do in this mission? We flew on the LADEE spacecraft, which is the Lunar Atmosphere and Dust Environment Explorer. It's actually a fairly small spacecraft, about 1.5 meters tall and about 1 meter in diameter. It was built by NASA Ames. It flew to the moon. In September of 2013, after about a month of transit, we were allowed to do our operations. And the very first attempt that we tried to do it, we immediately contacted the system and we're doing laser communications. And I'll talk a bit more about that. We've set records, of course, for both the download speeds from the moon at 600 megabits per second and also the upload speeds to the moon of 20 megabits per second, which allows us to send HD video, and I'll show you some examples of that later. We ended our operations in November of 2013, but then we turned it back on in April, and then the spacecraft itself, the mission was designed to crash into the moon, and so we crashed into the moon on April 12th of 2014, and our payload is in a little pile in a crater somewhere on the moon. But as I mentioned before, the data rate that we demonstrated back is on the order of 30 streaming HD TV channels, and that's from a distance of 400,000 kilometers. So it's a fairly significant improvement here. It's really a major leap, as I like to show in this chart right here. So we're getting this higher performance because we've moved from RF radio to light waves, where the frequencies are 100,000 times shorter, and so we can impart more data onto the beam. But the other thing is, as well, is that the wavelengths, the frequencies are higher, my apologies, by 100,000 times. And the wavelengths are, of course, 100,000 times shorter, and so that means that instead of a radio system where our beam diffracts out over large distances, we can narrow our beams. Diffraction is less of a problem, and so we can deliver more concentrated energy at a distance. And this is very attractive, of course, to NASA if you're going deep into the solar system. You want to be able to efficiently deliver signal power at a distance. And so how does that manifest itself? Well, if you look at this chart right here, the spacecraft in the top right corner is the Lunar Reconnaissance Orbiter. It flew to the moon in 2009. And these two images are to scale. Below, of course, is the LADEE spacecraft that we flew on. And on the top, you can see the Ka-band system that flew to the moon that was 100 megabits per second. That was state of the art at the time. Our mission, actually, our terminal on the spacecraft used half the mass, 25% less power, and we sent 6 times more bandwidth than the RF system could. Again, we're taking advantage of the fact that the shorter wavelengths allow us to have smaller apertures and lower transmit powers to make the swap of the system, the size, weight, and power of the system smaller. And of course, oops, hold on. Is there a back button here? Well, I guess not. Well, the red button. Okay, there we go. So, of course, this benefit of optical communications, being able to have these narrow beams and deliver more power efficiently, has a drawback, and it's the fact that these beams are so narrow themselves. And so our beam from the moon getting to the Earth is 6 kilometers in diameter. And so here's an example of the spot seen at White Sands, our ground station at White Sands. And 6 kilometers, you know, we tell folks, gee, 6 kilometers, it's a big beam, and they think, oh, that should be really easy. But you'll see here the scale of the problem. So we're stepping out an order of magnitude, and there's your 6 kilometer spot, and Las Cruces is nearby, about 25 kilometers away. And then you step out again, and there's a little dot there, if you can see it. Those of you with good eyes, there's a small red dot. You can see the state of New Mexico and the state of Arizona. Of course, there's the dot to help you out. And then you step out further, and there's our red dot. And of course, this is what the radio team has to deal with. Their pointing requirements are, of course, much looser than ours because their beam fills basically the entire western United States. And then, of course, the real challenge is doing it from the moon all the way back to the Earth. So the bottom line here is hitting a 6 kilometer target from 400,000 kilometers away is a real challenge. And so that was the big challenge that had to be really demonstrated here to prove to the agency and the world that optical communications was actually viable technology. So how did we do that? So this is the space terminal that was built by MIT Lincoln Laboratory. This is the optical head. It's a 10 centimeter, 4-inch aperture, collimated beam. Here's the beam coming out. It's actually, of course, filling the entire aperture, but my graphics people didn't realize that at the time. So what's novel about this is this 4-inch aperture is mounted on a 2-axis gimbal, but then there is a system inside that actually measures, it's an inertial reference system that actually measures the vibrations imparted by the spacecraft. So if I were giving this talk with a laser pointer, you'd see, you know, when I'm nervous, and I would have a very difficult time not making the beam dance. Well, the platform motions on the spacecraft, from reaction wheels and instruments, doors opening and closing, things like that, all cause micro vibrations, which can make that beam basically very challenging to place on that target on the Earth. And so the system here that was developed by MIT Lincoln Laboratory measures the platform jitter and then compensates for that jitter by just that amount. And so when we were doing testing at Lincoln, we actually tested it on a jitter table, and you'd impart the jitter and you'd see the beam rock solid. So it's a very impressive system. This is one of the breakthroughs that was required to make this work. I'm also showing here, these are the internal modules as well. We had 3 modules total. What you saw before was, of course, the gimbal telescope on the outside of the spacecraft. Inside the spacecraft, we have the modem module, which is about the size of a bread box. And that includes the lasers. And the laser system here is at 1550 nanometers. We're using commercial-grade telecom systems, erbium-based systems, both power amplifiers and preamplified receivers that we upscreen, of course, for the space environment. And we also have our encoding electronics here as well. Again, you've heard the rates that we've demonstrated before. We also have another module that's placed inside that's the controller electronics, and that is actually the brains for all the pointing, acquisition, and tracking of the system. And so here you can see the system fully integrated in LADI. You can see the optical module, which is in the gold MLI foil on the outside of the spacecraft, and a human for reference, of course. And then the modem module is embedded inside on the T. I don't really have a pointer up here to be able to show that. And then the controller electronics are there as well. So the system is integrated. We had a beautiful launch in September 2013 from Wallops Island, Virginia. We got to the moon a month later, and what were we able to demonstrate? So the first thing and the most important thing is the first attempt, we had instantaneous acquisition. We did not have to spend long periods of time hunting, scanning the beam and finding the spacecraft and making that work. It was immediate. And it was immediate on every pass we did after that. We never had a single issue with the pointing, acquisition, and the tracking. So this system is from that standpoint, was our biggest concern, and it was immediately demonstrated that it was not a problem. What happened next, of course, then we narrow our beams up and demonstrate both our high bandwidth downlink and our high bandwidth uplink. And I like to point out again that these are lasers at 1550 nanometers. We consider these eye-safe wavelengths, the kind of fluences that we're talking about. We had enough margin in the system that we could operate through thin clouds, and of course those who are familiar with optical communications will know that clouds are sometimes raised as a criticism. We have ways around that besides just having margin, of course. We were also able to demonstrate disruption-tolerant networking over the laser link, the lunar link, for the first time. We sent files back and forth. And that's because if you're dealing with clouds or other things that may give you a bursty system, then you want the ability to be able to buffer up and send data back down. And so not all applications are real-time. If you're allowed to have latency, then you can deal with this. And that's one of the ways that we get around clouds. Finally, the system that we flew actually had the ability to provide the range to the spacecraft at much better resolution than an RF system could do as well. So we had precisions that were better than a centimeter, whereas an RF system is on the order of a meter. And so from a navigation standpoint, it's a big help. So again, it was a big win to the spacecraft. But of course, we have to compete with the deep space network, the radio frequency deep space network that's talking to our spacecraft conventionally at the moon or Mars or Pluto coming up, of course, with New Horizons. And so other challenges, you have to be able to operate close to the sun. So we operated at full rate, downlink, within 3 degrees of the sun with no issues in broad daylight. And we were also able to operate when the moon was just above the horizon. And if you look there, you can see there's a lot of atmosphere in the path. This is not a coherent system. This is what we call the direct detection system, so we don't need diffraction limited optics, so we can basically collect the light, even though it's basically we're having a lot of scintillation in the atmosphere, and focus it down on our detectors and make it work. And of course, another secret of this is, of course, having very powerful error correction coding, and also having a channel interleaver, which allows you to disperse the code words across fades, because fading in the atmosphere, fading of the signal, is really the big drawback that we still deal with. And we were able to deal with that without errors in the system. Finally, I think the thing that we were most proud of is that we flew as a demonstration with the LADI team, and they sort of had an attitude of, okay, we're going to do our science on our spacecraft, your secondary really don't bother us. But our PI lobbied hard to make sure that they gave us a data connection from their buffer to us. And in the end, they wound up using us quite often to actually send data down, because their downlink from the moon was 50 kilobits on S-band. So we had them creamed by quite several orders of magnitude. The other thing we did, of course, was our...
Hello, this is NASA Administrator Charlie Bolden speaking to you through a pulsed laser beam transmitting data at 622 megabits per second from our LADI spacecraft currently orbiting the moon.
So that's HD video that we sent up on the 20 megabit per second uplink, looped back and sent down on the 600 megabit per second downlink. And you can see there are no errors in the system and the quality is beautiful. So we were very proud of this as well, and we did many other HD demonstrations with Bill Nye and other things as well. There are folks in the room here that were directly involved, and there probably would be some fun discussions after this. Feel free to contact us about some of the things we did. Now, one of the things I mentioned before is that clouds can be an issue, and so one of the ways around that, in addition to having a lot of margin, of course, is having site diversity. Because number one, you place your ground stations in places that generally don't have a lot of clouds to begin with, just like astronomers do with their telescopes. And then, of course, if you have multiple sites, that can see the moon, then you can pick and choose if one of them happens to be clouded up. And so our primary system was based at White Sands. That was built by MIT Lincoln Laboratory. But we also had a ground station provided by NASA JPL that worked with us. And then about a year and a half before we launched, the European Space Agency decided that they were going to join in as well. And they added the proper receiver and uplink lasers to their optical ground station in Tenerife. And they participated with us as well. So it was an international collaboration. So at this point here, I'd like to say that the success of LLCD was so apparent to a lot of the naysayers at NASA that they said, okay, let's see what we can do next. So our next steps here are actually funded efforts that I'm going to show you. These are things that are actually in the works right now. And so our first up is, of course, Deep-space Optical Communications. So this is a project that's being led out of NASA JPL to build a terminal to go to Mars. It's called Deep-space Optical Comm. And the first question might be, well, why are we not flying the LLCD terminal to Mars? And just to give you a point of reference, Mars is about 1,000 times further away than the Moon is, which is, of course, a factor and when you square that for the range loss, then it's a 60 dB more link loss. So you're going to have to do things a little differently than the design that we had for the Moon. You're going to need a bigger receiver on the ground. We had an 0.8 of a meter receiver on the ground effectively for LLCD. For this mission here, we're talking about renting time on the Mount Palomar Hale telescope, the classic telescope from the 1930s. And the plot that you can see here actually shows that when Mars is at its closest, we expect to be able to deliver about 250 megabits per second from Mars back to the Earth. Now again, compare that to the 6 megabits that I told you that we can do right now with Ka band and the RF. And you can see that we're doing very well. And also the size, weight, and power of the system that's planned right now is comparable or better than the RF systems that are being flown. So we're still in that same neighborhood. I do want to point out that some of the challenges, we had a beacon uplink of about 40 watts that we sent to the Moon for LLCD. In order to get a beacon signal out to Mars, you're going to need about a kilowatt laser to do that, for that to be seen because of the drop-off. And so we are in the process right now. We're funded, again, to space qualify a terminal by the end of 2017, which NASA will then provide as GFE, government furnished equipment, to the upcoming Discovery 2020 mission. And they are being encouraged with money, basically, to accommodate us, again, as a secondary payload and an experiment. And we hope to have a system flying in orbit around Mars in the 2022 timeframe when Discovery is launched, or after it's launched and arrives at Mars. But some of the technologies that we have to work on for this, we need more powerful laser transmitters because of, again, that range loss. The receiver and transmit aperture at Mars has doubled to 20 centimeters, which gives us another 6 dB of pickup in the link. The disturbance isolation system has to have even more rejection, again, because we have a narrower beam that we're pointing back to the Earth. And of course, we have to have a photon counting receiver in space to see that uplink beam. So again, we're proceeding very well on this, making good progress. Now, that's our deep space plan, but we also have a very active program in near-Earth optical communications. And so some of you may know that last year, NASA demonstrated the Opals mission. It was placed on the space station and demonstrated 50 megabits per second from low Earth orbit down to the ground. That's not the kind of data rates that we demonstrated from the Moon, but I do want to point out that Opals was actually a fresh-out program. The folks that worked that program, the rule was they were not allowed to be out of their school years by more than 3 years. So it's actually fairly impressive what a bunch of new folks did with this. And Opals has been fairly successful. We have some plans to do a few more things with it in the future, including putting adaptive optics on the JPL ground terminal that we have, and then trying those out to get light from Opals into single-mode fiber. But Opals is one of many missions right now, actually, that across the world for these low Earth orbit, direct-to-Earth missions. The links are shorter; they're 400 kilometers, so it's about an order of it's about 60 dB easier to do it from LEO versus from what we did at the Moon. So it really makes the system less constrained. So I have here in green boxes, of course, the Opals mission, and then there's a CubeSat mission that Aerospace Corporation is putting together for NASA's Space Technology Directorate called OCSD. We heard about that on Monday, and that's going to be launched next year. And then, of course, I have to point out fairly as well that ESA and DLR have actually been doing laser communications around the Earth since 2007. and actually the Japanese demonstrated in the mid-90s with ETS-6. So small demonstrations have been done, but again, it's been proven for short links, but you know, it's never been able to really break threshold and take off. And I think we're at that point now. And just to also note that ESA and DLR are now flying an operational system as well in near Earth. It's the EDRS system using optical communications as well. And there's been a lot of press releases on that recently. NASA's flagship mission for near Earth is a geostationary satellite relay mission called Laser Communications Relay Demonstration. We're launching it in 2018. It's a payload that's going to fly on a commercial Space Systems Loral communications satellite. We're delivering the flight payload, and we do have heritage here. We're using this. So the LLCD-based optical module and controller module that you saw in my images before for going to the moon, they are the same modules that we're going to use for this mission here. We're going to have 2 terminals on this satellite communicating with 2 stations on the ground. But what's going to be different is the modem is different. So before we used pulse position modulation, which is great in signal-starved environments, but we have links that are much shorter, and so we have higher photon fluxes in near Earth. And so we're going to differential phase shift keying, where you can basically push a lot more bandwidth. So this system that we're looking at is a user rate of 1.25 gigabits per second, and we can push it up higher as well, depending on what overhead rates we run in our error correcting codes. But that system, we're also going to have a high-speed electronic switch on board, so we can switch between the terminals and do some onboard switching as building out, so to speak, our first step really of being able to do optical networking in space. The ground stations are basically the stations that we used before, the JPL station at Table Mountain and the White Sand station, but we're upgrading them with adaptive optics, because when you go to phase shift keying or coherent systems, then you have to get your signal into single mode fibers for them to be demodulated in the receiver properly. So those are upgrades that we're doing. The other thing I didn't mention, or maybe I did, but the moon mission LLCD was only really slated for 30 days. We wound up operating for about 3 months. But LCRD here is going to be operating from 2 to 5 years, and that will really give us operational experience on how to use these systems. This is the architecture here again, 1550 nanometer lasers, the 2 ground stations with an operations center in the middle, again based heavily on at least the optics and controlling and pointing and acquisition and tracking that we did for the moon system. But you know, we don't want to just communicate between 2 points on the Earth. Really what we want to do is be able to use this geo relay system to communicate with satellites in low Earth orbit. And so we have a plan to take a modified version of an LCRD terminal and fly it on the space station in 2019. We're specifically looking at flying that on the Japanese evaluation experimental module, the GEM platform as it's called. It gives us the right views that we need, and in this image here in the box below you can see the terminal there. We actually have many more resources on ISS than we actually need for the size of the terminal. But we're working that heavily right now. That is a funded program. We do have technology development efforts. These are a little bit further away from flying. They're not flight missions yet. First of all, we'd really like to not have to rent time on the Hale telescope for our deep space missions, and so we're looking right now at a 12-meter ground station that would be able to support deep space, such as Mars or Europa missions, and bring back data. We're also, we've just completed a study about putting a small 5-centimeter aperture terminal on the Mars 2020 rover, which is essentially mechanically the same as the Mars Curiosity rover. It's going to have a new suite of instruments on board, but it seems like we may be able to squeeze on there as well. And for a direct-to-Earth link, which you'd be surprised about this, the RF system is an X-band system, and it does about 20 kilobits per second from the surface up. You can go through a relay and get more with RF, and sometimes that's done. But the system that we've looked at actually could provide an order of magnitude improvement of 200 kilobits per second from the surface of Mars. And if we get a relay satellite with an optical comm terminal on it that relays back, such as DSOC like we're looking at, then of course we could uplink 20 megabits per second from the surface of Mars up. So there's our NASA Glenn research facility is looking at integrating both radio and communications. This is for when we can't get mission designers to cut the cord, so to speak, from tried and true RF. So the ground rule that they have here is that it has to have the same size, weight, and power as the traditional RF system, but we're squeezing an optical system in as well. So what they're looking at is sharing the RF modem so that it would be software defined, so it could also drive an electro-optic system, sharing electronics and such. This is a fairly low TRL effort, but it's in work right now. Finally, I think it's important to ask, how are we going to infuse these systems into our networks? And I'm going to draw on a book, a kind of a classic marketing book from Silicon Valley here from the 1990s, Jeffrey Moore's Crossing the Chasm. This is a model for high-tech markets. I think this probably works for all of us in the room here for anything we're trying to do. But the curve you see is a Gaussian distribution of basically the population of customers. And so, of course, the main population of customers are the pragmatists. But off to the left, of course, are the innovators and the early adopters. And then, of course, the premise of this book is that there's a chasm that you have to cross to get the pragmatists to actually take your systems. Each group has different expectations for a new disruptive product. Innovators, they actually see a competitive advantage for using a new technology, and it lets them leapfrog their competition. But the pragmatist, which of course is the largest share of the market, they want a complete solution. They want a turnkey solution. For example, they're not the guys who get the Android phone, so to speak, and want to write their own code. They want an iPhone. They want to basically have it all there for them with a complete support network. And you know, NASA likes to pride itself, we think, on being on the cutting edge and being out there, but in reality, I find most mission managers are really pragmatists, and there are very few folks that will take the risk on and being an innovator. So how do you cross that chasm? And I'm coming down the stretch here. Basically, this is the whole product model. This is straight out of Jeff Moore's book. But I've adapted this to say, what are the things that we need to work on? And we are funding at NASA to try to make this work as well. So, of course, if you want a whole product to get customers to take this, to get my NASA missions to use the system, if there's additional software required, we have to provide it. And so we're actually working on DTN software. I said earlier that we had done a demonstration. And similarly, there's hardware that's required to support that DTN software. Buffer and burst edge electronics, for example, because we do have a bursty technology, we can buffer up the data and send it out. Systems integration, of course, that implies that you have calibration and certification test facilities. Commercialization. So as I alluded to earlier, in our case, we heavily leveraged the commercial telecom industry. We spun in, instead of spinning this technology out, we actually spun in what's being done in commercial telecom and used their components so we could build something that we could actually get components for and didn't cost us an arm and a leg, so to speak. So we're using that to drive the cost of these systems down, and we're actually fairly competitive with some of the high-end RF systems that are out there. Of course, ground networks are required, and so we're looking at expanding those as well, having weather stations and such. This is a key thing. The current NASA operational networks are not run by PhDs, they're run by technicians, you know, the folks that run the DSN and the space network that support all the RF right now. We have to be the same. We have to provide everything that's required for that. And then finally, and this is a big one, standards and procedures. So we have to comply with all the policy. The FAA doesn't want you shooting lasers around in the atmosphere without their approval. And there's something called the Laser Clearinghouse that cares a lot about that too. And of course, we'd like to interoperate with other agencies because there's a lot of cross-support and cost-sharing we can do. So with that, I'm going to go into our fun chart from my organization, which is Space Communications and Navigation. My organization that I work for, I'm the tech development lead, but the operations folks that live there, they actually provide all of NASA's current networks. So the Deep Space Network, the Near-Earth Network, and of course the space network. So you can see that here, the TDRS satellites. And there's a blue link here, and that's our first LADI LaserCom link. So I'm trying to push those links in. So going forward, we have plans for LCRD, as I talked about earlier, rolling in there, and of course a mission to Mars, the DSOC mission. And then in the future, we see that evolving even more. I don't ever see RF going away. I see us complementing them. You know, until we can invent the optical omni antenna, we're always going to have an RF system in case your spacecraft's tumbling. But I can see this being the high bandwidth system and the low bandwidth, low gain system being the RF system. And at this point here, that's kind of our vision slide. And I think I'm done at this point. So thank you.